This is Himabindu, Assistant Professor in IARE College. So today in this video, I would like to explain the problems on regular expressions and regular languages. So here, this is in the second unit. So question bank discussion. We are going to discuss on question bank. So how many types of problems we have in the regular expressions and how to convert the finite automata into regular expressions and regular expressions to finite automata. We have to discuss in this video. So coming to the regular expression. So what is meant by regular expression? So expression is describe the language accepted by the finite automata. So the languages which are accepted by the finite automata is named as a regular languages. So here the with the languages what we are going to express. So what we are going to design the language in a systematic way that is named as a regular expression. So the language accepted by the regular expressions are referred to as a regular languages. So here both are vice versa. So with regular expressions are the languages which we are going to use for the construction of regular expressions or regular languages. And regular expressions are used to check and match the character. So why we are going to use this patternized expression in the sense to check the character combinations in the languages. So here in the languages we are having the strings combination. So to check whether the string is in the same pattern or not, in to represent that language in a systematic way, we are going to represent the language in a regular expression form. And here alpha is nothing but so it is an alphabet. So the string which is going to be formed with the input symbols named as a alphabet. And here the regular expressions are so how we will design. So in finite automata we have the capital letters like the states and input symbols are there. But here in the regular expressions, we have only the terminal values like here A or A plus B like this. So there is no states in this one. So why? Because this regular expression is can be expression over alpha. Alpha, sorry, sigma. Sigma is nothing but it is a combination. It is having the input symbols. So those are represented as a alphabet. And here the regular expressions have some properties and some rules here. So to design the regular expression, so what we will consider as a regular expression, the pi which is nothing but the empty which denotes the empty set, so which denotes the empty set is also a regular expression. So regular expression is equal to pi is also, this one is the single one is also a regular expression, and like that epsilon is also a single expression. So regular expression or regular expression is also single, epsilon is also a regular expression, and like that it's a combination of sigma. So in the sigma if we have zeros comma ones or a comma b and so on, how many inputs are there, we can form the regular expression with this the sigma symbols. So that is named as x here. So E is a regular expression and denotes the set of x. So if we have to represent that value c comma b comma, in case of two things are there, we need to represent like this. So this is the set. So regular set, we can represent it as a regular set. So these kind of alphabets are also this kind of alphabets are represented in the regular expression. So this is about the regular expression. And what is meant by regular grammar? So grammar generally we have the four tuple notation. So one is G is equal to V S T P. So for every grammar, if you take regular grammar or context free grammar or unrestricted grammar, so whatever the language, whatever the grammar is there, we have to represent that in the four tuple notation form. So in this four tuple represents, so V is nothing but the states or finite number of states, and S is nothing but the start state, and T is nothing but a terminal symbols, and P is nothing but a production. So here we have to represent a grammar, finite or grammar in this four tuple notation only. So like this regular grammar also we have this four tuple notation, and here coming to the regular grammar. So what is the hierarchy number? So this is the type 3. So this is the regular grammar or G, and this one type 2 is a push down automata, context free grammar, and type 1 is a context sensitive grammar, and type 0 is a unrestricted grammar. So these are all the four types of grammars we have. In this one we are talking about the regular grammar. So regular grammar is a type 3 grammar. So this type 3 grammar is named as a regular grammar and generates the language, regular languages, and the construction. So it's construct the finite automata. So this is about the regular grammar, and they have a single non-terminal on the left hand side. And what are the rules to follow for the construction of regular grammar? So right hand side only we have the single non-terminal value like S tends to A like this, and right hand side consisting of single terminal or single terminal followed by a non-terminal. So here these are the only examples to express these regular grammar. So here either single terminal or it is followed by the terminal followed by the non-terminal. Single terminal followed by the non-terminal is the two types of production rules we will discuss in this regular grammar. And how the form, so how these productions are in this form. So here A tends to terminal followed by capital letter non-terminal. Only single terminal is also accepted, and it's also combination of non-terminal followed by the terminal. So here in this one we have two types of grammars. So one is a left linear grammar and right linear grammar. So how to represent by seeing the grammar, how we can say that it is a regular left linear grammar or right linear grammar. So let me write the examples of this left linear grammar. So S tends to A, capital A, and A. So this, if you observe, the non-terminal is right left hand side. So non-terminal, whenever the non-terminal is left hand side, we can say that it is a left linear grammar. And like that here, right linear grammar, S tends to, same example, we will write it here like this. So here the capital A, which is right hand side. So right hand side is there. So that's why we can represent it as a right linear grammar. So these are the two types of regular grammars we have. So in this one, a left linear and right linear. So how to represent this left linear non-terminal is the position of non-terminal will decide the grammar whether it is a left linear grammar or right linear grammar. So this is about the regular grammar, and moving to the examples. So here we have taken some of the examples from the question bank, and we are going to discuss how to convert one form to another form. So here is the regular expression. So the input is a regular expression and we need to convert it to a regular grammar. So the from regular expressions to regular grammar, how to convert this one? So here we have the example of A plus B. So first we need to design this into a finite automata. So how to design this into a finite automata? We'll take first one A plus B whole star. So finite automata, we have to design the finite automata. So finite automata is, so here if you elaborate the language, so with the single A or A plus B whole star. So A plus B whole star in the sense, so let me write A plus B whole star expression language. So epsilon A comma B comma and AA or AB and BA or BB and so on. We can. So here so first element is the epsilon. So here with the so whenever we have the kind of expression, so with the single a also, we are going to reach the final state. So that is how we are going to write. So here instead of this a plus b, first element a epsilon. So what is the thing we have to ensure with the single a q naught, with the single a, it is reaching the final state qf. And here we have to design this regular expression. And if you take, so here a r a b a and b a and so on. So this is the language for this expression. So here first one is a, and here we need to write this a plus b whole star finite automata. So here with this a plus b whole star finite automata, so here I will write it as a comma b. So this is the simply with the single a plus b whole star finite automata. So why? Because the first one is the epsilon. So first input is also epsilon, so that it is reaching the final state. And for the two more input values a comma b, it is reaching multiple times of a comma b input. So it is reaching the final state. So this is the expression, regular expression, finite automata for this expression. And we are just combining these together and we are writing. So this is how we are converted the regular expressions to finite automata. And now we need to write the transition functions first. So here transition of q naught comma a, it is reaching the qf, and with the and q for q naught qf, we have the value of a is there, and it is reaching the qf only. And transition of qf comma b, it is reaching the qf only. So with the three inputs, it is reaching the final state. And now we have written the transition function. So we need to write the production rules. By seeing this transition functions, we can write the production rules. So here one thing we need to observe, we have the condition. So whatever the so q naught is equal to, I am writing the terminal like s comma qf is equal to a. S. So why? Because every grammar which starts with the S capital letter, start symbol. So S tends to A. So with the input symbol A, it is reaching the capital A. So that is the final state. And when with the one input symbol, when we are reaching the final state, we need to add the S tends to small a also. This represent, with this input symbol, it is reaching the final states. So whenever we are reaching the final state from one state, so we have to write the terminal, single terminal symbol also, so that it can represent the with this terminal, it is reaching the final state. So here final state is a. And for this thing we have written like this. And for so we have to take one more state, a. A tends to a, it is reaching a. A tends to b, it is reaching b. So here we have the things like this. So let me write the same thing. S tends to a, capital A, seminar also. And here also A and B also we need to write. A tends to A, B, A and A comma B. So like this we need to write the transition. So here we need to write the grammar for this one. So here how we have converted the regular expressions to the regular grammar. So this is about the first one. So a plus b whole star. So here this is the regular grammar. So we have these are the production rules, and if you want to write all the grammar together, we will write v is equal to here s comma a and t is equal to a comma b, and these are the pre-productions, and s is the start symbol. So with this we can say that the grammar of this regular expression is this one. So and let me solve the another example. This is the first one. And for like this, first we need to convert the regular expressions to the regular language, and now converting into a finite automata, and through the transition functions we can represent that in a regular grammar. So second one, so we have the two choices. So here second one, the A plus AA plus BB. So AA plus BB, it is reaching the final state. So what this the A plus B, if you observe A plus B, so with the A input or B input, it is reaching the final state. So this is the thing. So here also one more AA or BB. So with the double A's or double B's, it is reaching the final state. So how to represent this in a finite automata? So here initial state is the Q naught, and with this A and A, it is reaching the final state, and QF. And here also A, B, B, it is reaching the final state. So this is the simple expression, simple finite automata for this AA plus BB. So here if you want to insert any values like Q1 and Q2. So here these are how to represent this in a finite automata. So how to represent this in a regular grammar. So regular grammar. So regular grammar, so we need to write the transition function first. So transition functions, so delta of Q naught comma A, it is reaching the state Q1, and Q naught comma B, it is reaching the state Q2, and delta of Q1 comma A, it is reaching the final state QF, and here we and delta of Q2 comma B, it is reaching the final state. So these are the four regular transition functions for this regular so finite automata, and we need to convert that into a transition regular grammar. So here this expression, so Q naught Q1, so we have to name it as a capital letters. So here we will name this Q naught as a S. So here Q naught is equal to S, and Q1 is equal to A, and Q2 is equal to B, and QF is equal to F. So here we need to write, so S tends to A, it is reaching the value A, and S tends to B, it is reaching the value B, and here, and one more, S is already finished, two input symbols, and we need to write for A tends to A, it is reaching the final state. So B tends to B, it is reaching the final state. And here we need to write the final state so that, so they both two are reaching the final state, in the sense we need to write the terminal values also. Here B. So here altogether we will write this S tends to A, B, B. And S tends to A, F, A. Sorry. A tends to AF and B tends to BF, B. So these are the regular grammar for the given regular expression. So like this we need to convert the first regular expression into a finite automata, and then by seeing the transition functions we can write the production rules. So these are the regular expressions. And here coming to the, we have written the transition. Earlier we have given the input as a regular expression, and here they have given the regular finite automata. So this one we have to convert into a regular expression. So for this example, we have to choose the identity rules for the construction of regular expressions. So here those are already discussed in the previous videos. So here first we need to construct, by seeing this transition functions, we need to convert into a transition diagram. So first transition diagram. So how many states are there? 3 states are there. So that initial state is, so initial is Q1. Final states are 2 states are there. So 2 states are there we need to represent. So initial is a Q1 and Q1, Q2 and Q3 is there. So this is a final state and this is also final state. So Q1, Q2 and Q3 are the final states. So from Q1 state, so we have transition functions. Whenever we are giving 0 as an input symbol, it is reaching the Q2 state. And here from Q1, one input, it is reaching the Q3. And from Q2, whenever 0 is there, we need to, whenever 0 is there, it is reaching the state Q1. And from Q1, Q2, 1 is input, it is reaching the Q3. And from Q3, 0 input, so 0 input, it is reaching the Q2 value. And here Q1, 1 also, it is reaching the value Q2 only. So this is the transition diagram for the given example. So first we need to write the equations for this one. So how to write these equations in the sense, by seeing this transition diagram, whatever the incoming edges for every state, so we need to write like that. So here how to write that one. So here we have the Q0, Q1 is there. So Q1 is equal to, what are the incoming edges for this Q1? So incoming edges in the sense, so this 0 with the state Q1, Q2. So we need to write this as a one equation. So no more incoming edges for this starting state Q1. And Q2, we need to write the Q2. And for this Q2, what are the incoming edges? 0 Q1 and these 2 are there. So 1 plus 1 Q3 and 0 Q3. So here we can write it as a 0 Q1 plus 1 Q3 common 1 plus 0. So this is one equation and this is second equation, and we have one more Q3 state. So from Q3, so what are the incoming edges? Only, sorry, from Q1 it is reaching the, so with the input, this is also incoming. We have the two equations. So what are those? So 0 or 1 Q3 plus, so here 1, from edge Q1. So Q1, 1 Q1 and here 1 Q2. So 1 Q2. So here this is the third equation. We need to solve this one. So here we have the two final states, so that we need to write like Q2 union equation Q3. So this represents the two final states union together. So we have to combine this regular expression and this one with the union operation. And first we need to solve this by using the transition, so by using the identity rules. So here after this one, first we need to solve Q1 is already there, and we need to solve these two equations. So Q2, whenever we have to take the Q2, so Q2 is there, and Q2 when we have the Q1 and Q3. So Q1 and Q3 is there, so that if you substitute the Q1 value, it is in terms of, so Q1 value is equal to 0 and 0 Q2, and remaining same we need to write like this. And here we have the expression like Q2 is there, and 0 0 Q2 plus Q3, 1 plus 0. So here R is equal to P plus RP. So R is equal to Q plus RP is equal to R is equal to QP star. We need to write, this is the Adam's theorem. So we have to solve this one by using this Adam's theorem. So we have to left hand side. So we have to remove the right hand side of non-terminal values. So how to remove this one? So here 0, 0 is there, and we need to assume like this equation, and we need to try to remove this one. And so Q3 is there, and for this one, if you substitute 0, 0, Q2, and here Q1 is already there, and if you substitute this, if you solve this Q3 equation, we will have the equation in terms of, so Q3 is equal to 1, Q1 is there, 1, and this is in terms of 0, Q2, and 1, Q2. And if you take the common Q2, so Q2 as a common, 1, 0 plus 1 is the thing. So this is the fourth equation we can assume. So here Q3 is this one. And instead of this Q3, if you substitute this value, Q2, 1, 0, 1, along with this one, 1 plus 0. And here substitute Q, and now here the common thing is a Q2, 0 plus 1, 0, 1 plus 1 plus 0. And here we have this expression R is equal to R plus, so Q plus RP, so is equal to R is equal to QP star. So this is the Adam's equation. So we have to convert this into in this form. So here, if you think epsilon as a P, so epsilon as a P, so this is the P, and this is the R, and this is the Q. So this is Q2. So R is equal to R P, RQ plus P. So what is the expression? R is equal to QP star. So here R is equal to now Q2, P star. P is nothing but epsilon, and star, Q star. So Q is the only in terms of terminal symbols only. 1 plus 0 whole star. So epsilon into anything, epsilon into R, according to the R dot epsilon is equal to a R only. Like this, with this expression, we will get only the single value, 1 plus 1 and 1 plus 0. So this is the whole star. So this is about the Q2. So Q2 is this one, and we need to solve this equation with the Q3. So if you substitute this entire thing here is the Q2 value, we will get all together. So here, let me erase this one. So here, what is the value of, this is equation number 5, and we need to substitute this Q3, Q5 value in the 4 value. So what is the value of Q2? So 0 plus 1, 0 plus 1, 1 plus 0 whole star. And here we have 1 0 plus 1. So this is the Q3. And here we need to union Q2 union Q3 is the 2 or the final state. So that again I need to write Q2 is equal to, so this one, and 0 plus 1 0 plus 1, 1 plus 0 whole star, 1 1 0 1 1. So this is a Q2, and we need to union plus, again we need to write this Q3 value, 1 0 1 1 plus 0 whole star. So this is a regular expression for this given finite automata. So like this we need to convert the, first we need to write the transition diagram, then we need to write the equations by seeing the diagram, what are the incoming edges for the every state, and then we need to solve the equations one by one by using the identity rules. So this is about the second one. And third one, 0 plus 1 whole star and 1. So how to write the two grammars. So left linear grammar and right linear grammar for the single expression. So here regular expression is the input, and now we need to convert into a grammar. So earlier we saw that we have seen that expressions, finite automata into regular expressions to the grammar, and here they are asking for the right linear and right linear grammars. So first step is same finite automata we need to construct. So here 0, 1 star plus 1. So we need to write the, so Q naught is the initial state, and if you solve this one, so with the 0 input or 1 input, it is reaching the final state. So, and with the multiple 1 star. So here how to write this one? Q1. So here 0, 1 star plus 1. So with the 0 input, it is reaching the final state, and with the 1 input also it is reaching the final state. And here, this is the final state. And here 1 star, we can write it as a 1 star here. So this is the finite automata for this regular expression. And now we need to write the transition functions. Then we need to write the linear grammar. So transition function delta of Q naught comma 0, it is reaching the QF, and delta of Q naught comma 1, it is reaching the final state, and delta of QF comma 1, it is reaching the QF only. So we can convert this into a grammar, that is nothing but production rules. So let me write Q naught as a S and QF as a A. So here S tends to, with the 0 input, it is reaching A, and with S tends to, with the 1 input, it is reaching E. And here also with the A input, with the 1 input, it is reaching the final state. So if you here observe this 0 and 1, so why? Because all inputs it is reaching the final state, so that we need to write the terminal values also. And 1B, 1A, so 1A, it is reaching the final state with the 1 input. So altogether we will write it as a 0A, 1A, 0 input or 1 input, and A tends to A and terminal. So this is how we have written the production rules. So by seeing these values, so the terminal values, so the non-terminal values, the capital letters are in the right hand side. So this is the right linear grammar. So right linear grammar. So we have the right linear grammar, and now we need to convert into a left linear grammar. So how to convert the left linear grammar? We have the steps like, first we need to interchange the positions of initial and final state. Initial and final states. So changing the initial state and final state. So now here this is the QF and this is the Q naught. So this is the Q naught. And we have to write this final states also changed here. QF. This is the incoming edge, this is the final state. And now we have to reverse the edges. So reverse edge. So loop is same as it is, and we need to reverse. So 0 is representing to Q1. So now it is represent to 0, and this one also it is reaching the 1 value. So here, and then we need to write the third step is we need to write the delta transition function, and fourth step we need to write the production rules, and fifth one change the positions. Change positions of terminals, non-terminals. So first one is what we have to do, delta of QF comma. So we have to initiate with the QF. So initial one is the QF. And what are the incoming edges? So no incoming edges. So with the 0 input, nothing. So 0. So QF tends to 0 is pi. So, and we need to start with the transition of Q naught comma 1. It is reaching the Q naught, and delta of Q naught comma 0. It is reaching the, with the Q naught 0, it is reaching the QF, and delta of Q1. So here with the one input, it is reaching the two states. So two states. So here, and this is the transition functions. Now we'll convert this as a and this one as a S. So S tends to 1, 1, 1 S A. So 1 S, 1 A, and S tends to 0 A. So this is the, and whenever it is reaching the final state, we need to write the terminal values also. So this is the input. So this is the, and now we need to convert into a position. So productions we have written and change the positions here. So A is to be changed here, and this A also, first terminal and followed by the terminal, and here also A 0 0. So this is how we got the left linear grammar and right linear grammar. So these are the steps we need to follow for the construction of left linear and right linear grammars. So this is the third example, and here epsilon NFA. So we have to design the epsilon NFA for the regular expression. So here for every NFA, we need to write the starting and ending epsilon symbol. So in between the epsilon closure of every input, how the NFA is going to be designed. So here we can divide this into two things like this A plus A, B plus A whole star and A star. So here for single A star, how to write the epsilon NFA. So here this is the state and this one is the C state. And with this, it is reaching the one state. So here this is the normal thing. So normal finite automata. When coming to the epsilon NFA, so epsilon NFA, we need to draw the epsilon symbol, and here with the epsilon input, it is reaching the one state, and with the epsilon symbol, it is reaching the final state. And here also epsilon, and this one also epsilon. And here this is the epsilon. So this is for the A star, and like this we need to write for the B plus AA whole star. And how to represent? So here start state and epsilon, and here so two choices are there. So one is a B input. So here epsilon. So one is the B input and it is reaching the one state, and here A is there. So that I am taking one more state. It is reaching the epsilon. So epsilon. So here this A, and here also epsilon. And when we observe, and here epsilon. So epsilon symbol. So here it is the final state. So initially it should be like this epsilon, and here we need to all together epsilon closure here. So epsilon closure we need to write. So like this we have to combine. So why? Because it is a concatenation operation. We need to combine these together. Then we will get the epsilon NFA for this regular expression. So let me write this expression. So first initially. So same thing we need to write. So here we need to write, and this one. So it is not a final state. Why? Because A we need to enter. So this is the B. and this is A, and these are all the epsilon symbols. So epsilon symbols, and here also epsilon symbol, and here we need to start from here. So with the epsilon symbol, it is reaching the one state, and here A, and here final state. So here A input, and here epsilon. So epsilon, and so here, so one more state is required here. So here epsilon, and for this one we need to write the thing epsilon, and here we need to write the epsilon symbol. So like this we need to write the epsilon NF for regular expression. So epsilon closure we need to write, and when we have to combine together, so it is a concatenation operation, so that we are writing the value, so combined together as a one finite automata. So this is about the regular expressions and regular languages grammars. So these are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.